In section 4, RSA and stereoselective preparation of alkenes, will start in section 4.1 by looking at stereoselectivity and the Wittig reaction. And the Wittig reaction is perhaps the most versatile and general method for making CC double bonds. So here is an outline of the Wittig, where we have a phosphonium ylide reacting with a ketone, or in this case an aldehyde, to form either an E or a Z alkene. And phosphonium ylides can be divided into stabilized ylides and unstabilized ylides, depending on the nature of the substituent on the carbon atom of the ylide. So for stabilized ylides, we have the R group here as an electron withdrawing group, such as an ester, which stabilizes the adjacent negative charge through resonance. For an unstabilized ylide, we classically have an alkyl group bonded to the carbon bearing the negative charge. And so here this alkyl group, which is plus I, pushes the electron density towards the negative charge, destabilizing it, hence the term unstabilized. Unstabilized ylides are prepared by deprotonation of a phosphonium salt using a relatively weak base. It can be stored, many are commercially available, and although they react with aldehydes, they're generally unreactive to ketones. Stabilized ylides react with aldehydes to give mainly E or trans alkenes. So we're now going to look at the synthesis of E1-pent-1-enyl benzene, which uses a stabilized ylide. Here's my target molecule. We're going to disconnect the carbon-carbon double bond. We've got two different possibilities, two sets of reagents, either this unstabilized ylide reacting with benzaldehyde, or alternatively butanal reacting with this stabilized ylide. This is a stabilized ylide because the negative charge can be delocalized around the benzene ring. And it's this combination that works to form the E isomer, because this particular ylide is stabilized. So in the forward reaction, we'd make the stabilized ylide from benzyl bromide. We'd start with a nucleophilic substitution using triphenylphosphine to make a phosphonium salt. We then deprotonate the hydrogen on this carbon using a relatively weak base. The stabilized ylide will then react with the aldehyde to form mainly the E alkene isomer, the one we require in this synthesis. Formation of the E isomer is predictable because the E isomer is thermodynamically more stable than the Z isomer, and this selectivity may arise from reversible formation of two possible betanes. So here we're looking at the reaction of this stabilized ylide. The ester stabilizes the negative charge with an aldehyde, and on nucleophilic addition to the aldehyde we can form these two different betanes or betanes. And this erythro-betane, the two bulky groups as drawn here, are on the same side. On the erythro-betane, they're on the opposite side. And as you might expect, when the minus reacts with the plus to form the four-membered ring, four-membered ring would be much more strained if the two substituents are on the same side. So the reaction leading to the Z alkene is much slower. So we can go back to the starting materials, then form the threobetane with the bulky groups on the opposite side. Formation of the four-membered ring now is much faster, and then this then reacts to form the E alkene isomer. Let's now look at non-stabilized ylides, which are formed by deprotonation of a phosphonium salt of this type here, and now we need a strong base. Unstabilized ylides need to be formed and used immediately. They react with both aldehydes and ketones, and they react with aldehydes and ketones to give mainly the Z alkene, and the reason for this is not entirely understood, although there's a nice discussion of this in the Claydon book. So let's now look at an example, the use of an unstabilized ylide to prepare 3Z5E non-3,5-diene. So here is my target molecule. I'm going to be looking at constructing this Z double bond at the 3 position. Let's disconnect the CC double bond through our Wittig transformation, and we get two sets of starting materials, either this unstabilized ylide together with this aldehyde, or this aldehyde here together with this stabilized ylide. We can delocalize the negative charge through the carbon-carbon double bond. Because this is an unstabilized ylide, when it reacts with the aldehyde, we'd expect to get mainly the Z alkene, so this will be the combination of reagents that we're going to use in this synthesis. So we start by making the unstabilized ylide in 2 steps. We take 1 bromopropane with triphenylphosphine, we form the salt, and then we deprotonate one of these hydrogens using a strong base such as butyl lithium. The unstabilized ylide will then react with the aldehyde to form mainly the desired Z-alkene. As stabilized ylides are unreactive to ketones, there is a variant of the Wittig reaction called the Horner-Wadsworth-Emmons reaction that can be used, and this method uses a deprotonated phosphonate ester. It's negatively charged, and as a consequence it's more reactive to CO double bonds than a phosphonium ylide, which is neutral. And also water soluble byproducts are formed, and these are easily separated from organic products. And reaction of these stabilized phosphonate ester anions with aldehydes or ketones gives mainly the E, or the trans-alkene. So here's an outline of this reaction. In the Horner-Wadsworth-Emmons reaction, or the HWE reaction, you start with a phosphonate ester. On reaction with a base, you form this anion here, and it's this negatively charged enolate ion that reacts more rapidly with the carbonyl groups, or react with an aldehyde or indeed a ketone, in this case cyclohexanone. We get nucleophilic attack to the oxygen, and then the mechanism is reminiscent of the Wittig reaction, leading to the formation of a carbon-carbon double bond as shown here, and the byproduct is this water-soluble charged ion, which can be easily removed from the organic product. Let's now look at section 4.2, where we're using alkyne anions and then stereoselective reduction to form alkenes. So these alkyne anions here, where we have a negative charge on a carbon in a triple bond, are formed by deprotonation of terminal alkynes, typically using NaNH2 as the base. And alkyne anions are strong nucleophiles. They react with a range of electrophiles to form carbon-carbon bonds. The carbon-carbon triple bond can be reduced to form alkenes stereoselectively. To form a Z-alkene, we'd use hydrogen Lindelof catalyst. To form an E-alkene, we'd use sodium and liquid ammonia. So let's now have a look at an RSA. Here we have a Z-alkene, here we have an E-alkene, and we can recognize that we can make either of these by going back to the corresponding alkyne. We can make an alkyne of this type by disconnecting one of the side chains, put a plus on the side chain, a minus on the triple bond to give us this alkyne anion, which can be formed on deprotonation of a terminal alkyne. So we'll now look at an example of this, namely to make E-pent-2-ene-1-ol. And here is my target molecule, this E-alkene. We're going to recognize that the E-alkene could be formed from the corresponding alkyne. So we go back to the alkyne. We're now going to disconnect this side chain bearing the OH group. We're to put a plus on the side chain, a minus on the triple bond. Synthetic equivalent for this will be methanal or formaldehyde. The synthetic equivalent for the anion will be the corresponding terminal alkyne together with a base, NaNH2. So in the forward reaction, we take the terminal alkyne, we deprotonate it, we throw in methanal, we then add in acid to protonate the oxygen to form the primary alcohol, and then we get stereoselective reduction of the triple bond using NaNH3. We'll now look at a more complicated example, namely E-dodes-10-enyl acetate, which is a P-moth pheromone. And here we have an E-alkene at one end and an ester at the other end. So we're going to look at our RSA by disconnection of the ester first of all, back to O- and a plus on the carbonyl. Synthetic equivalents for these will be an alcohol, and then we need to put a leaving group on this carbon, so in this particular case we can use an acyl chloride. Let's now think how we can make this alcohol with the alkene at the end. We can imagine we can make the alkene from the corresponding alkyne. So we now go back to the alkyne. We disconnect the carbon-carbon bond to give this alkenyl anion and a positive charge in this molecule. Synthetic equivalent for the alkyne anion will be the corresponding terminal alkyne. The synthetic equivalent for this positively charged species will be where we have a leaving group, such as a bromine at this position here, namely 9-bromo-non-1-ol. Now in the forward reaction we have to be careful, because if we take the anion from prop-1 ion and react it with this bromide, rather than getting substitution of the bromine atom, we'll get deprotonation of the alcohol because we have an acidic hydrogen atom here. So in the first step we would need to protect the OH group to stop deprotonation taking place. And that's what was carried out in this forward synthesis. First step would be to protect the primary alcohol using TBDMS chloride and a base to mop up the HCl, and we get this silyl ether, which is stable to nucleophiles and bases. So we can now take the alkyne anion and we can do an SN2 substitution reaction on the primary bromide. We can then stereoselectively reduce the triple bond using sodium and liquid ammonia to form the E-alkene. And then we can remove the protecting group using TBAF and then convert the alcohol into the desired ester using ethanol chloride and a base in a classic nucleophilic acyl substitution reaction. Let's now move on in section 4.3 and have a look at the palladium zero catalyzed coupling, the so-called Heck reaction. And in recent years, a number of important carbon-carbon bond forming reactions, including the Heck reaction, have been developed using palladium zero catalysts. The Heck reaction can be used to form a di-substituted alkene from a terminal alkene and an aryl halide, or alternatively a vinyl halide. The carbon atom bonded to X, which is your halogen, must be sp2 hybridized. And for the reaction mechanism, you can have a look at this in the Claydon book. So here is the Heck reaction. We're taking an aryl or vinyl halide here, where X is typically bromine or iodine. We've got a terminal alkene. In this case, it's monosubstituted. We're reacting it with a palladium zero catalyst, and we're going to lose HX from these two reagents. We're going to lose an H atom from the end of the alkene. We're going to lose the X here from the vinyl or aryl halide, and we're going to form a di-substituted alkene. So the monosubstituted alkene is converted into a di-substituted alkene. The nice thing about this reaction is the alkene can be electron poor, electron rich, it can be neutral, and the reaction is highly selective. The regioselectivity is explained by the R group being introduced at the least hindered end of the carbon-carbon double bond, and the stereoselectivity is explained by the formation of the more stable E alkene, with the R groups here and here on the opposite side of the CC double bond. So let's now look at a couple of examples of this. You can make methyl cinnamate by disconnection of this carbon-carbon bond using a Heck reaction. In our RSA, we can go back to bromobenzene and methyl acrylate. In the forward reaction, we use our palladium catalyst together with a base. We lose a hydrogen atom from the alkene, the bromine from the bromobenzene, and we couple the two together to make this new carbon-carbon bond. One final example here, this dienone. I'm going to disconnect this carbon-carbon bond here in between the two CC double bonds. I'm going to put an iodine at this position. We're going to now start with methyl vinyl ketone. These two are readily available starting materials. We lose a hydrogen atom from the alkene, an iodine atom from the vinyl iodide in the presence of your palladium zero catalyst, and you make your desired product. And you'll notice in both cases we get the E isomer of the alkene that's formed, because these bulky substituents here and here land up on the opposite side to these carbonyl groups.